Hi, my name is Scott Hogue and I am double majoring in philosophy and computer science. I also have a background in mathematics and theoretical physics. I first became interested in programming in 4th grade when I wanted to do nothing but make video games. I discovered QBasic and right away began to learn the ropes of game programming. My interest in programming also led to my learning trigonometry to develop a 3D engine. In a few years, I hope to be developing business software and writing a few modules applicable to both the academic and gaming worlds. I also hope to be an author and write about several subjects including mathematical philosophy. My presentation is on Z notation, which is a useful way of describing the behavior of a software system that is based on our current understanding of mathematics. I found Z to be very inspired and would not be surprised if it becomes a highly successful specification language. Let's get started in understanding Z notation. This brief introduction will provide an overview of what Z is about and offer an example of how to use Z to model a system. What is Z? Z is a model-based notation that was conceived in the late 1970s in collaborative projects between Oxford University and its industrial partners. An official Z standard was released in 2002. Z is not a programming language. It does not compile into executable code and it does not run in an interpreter. The purpose of Z is to describe the behavior of a system, such as a software application, in the language of modern mathematics. The predominant foundation of modern mathematics, also used in Z, is Zermelo-Fraenkel set theory. So let's begin by looking at Zermelo-Fraenkel set theory. Zermelo-Fraenkel set theory, commonly abbreviated ZF or ZFC, is a language used to describe the properties of sets, that is, aggregates or collections of objects. Zermelo-Fraenkel set theory has become so mainstream as a foundation of mathematics that it underlies every branch, including algebra, calculus, and discrete mathematics. As modern physics is based on a mathematical description of nature, it also has its ultimate basis in Zermelo-Fraenkel set theory. Zermelo-Fraenkel set theory is based on 7 core axioms. These axioms are used to deduce the truth of further mathematical statements, which form the basis of all subjects in mathematics taught in schools. All of them are stated in the symbolic language of first-order predicate logic. Let's review symbolic logic. Symbolic logic contains subjects and predicates, which express relationships between objects and their properties. Logical negation, which expresses the untruth of statements. Logical connectives, such as and, or, and implies, which join statements in well-defined ways. And quantifiers, which use a variable to express general laws or statements of existence. Now let's take a look at the 7 core axioms of Zermelo-Fraenkel set theory. The axiom of extensionality states that any 2 sets with the same members are to be considered as equal. The sum axiom states that for any set A of other sets, one can form another set C comprised of all elements belonging to the sets contained in A. The power set axiom states that given any set A, one can form the set B of all subsets of A. The axiom of regularity states that no infinite descending chain of nested sets is possible. The axiom of infinity states that there is at least one infinite set. This axiom allows us to form our concept of the number system. The axiom of cardinals pertains to different sizes of infinity. 2 infinite sets are considered equal in size when their respective objects can be placed in one-to-one correspondence. Otherwise, the infinities are of unequal value. Finally, the axiom of replacement states that for any functional predicate phi, one can apply the functional predicate to all elements of a given set A, transforming it into a new set B consisting of the resulting values. Certain expressions in Zermelo-Fraenkel set theory, which appear as common mathematical notation, serve as abbreviations of the often much more complex logical formulas that underlie them. In order to clarify the ambiguity in these notations, Z notation offers a more definite syntax to denote these expressions. This also facilitates type checking by computer software in the process of describing a system. Every expression in Zermelo-Fraenkel set theory has a corresponding equivalent in Z notation. Why use Z notation? Although UML and data flow diagrams are useful in modeling system behavior, there are limitations in the amount of detail that they can describe. Given the expressive power of modern mathematics, it is natural to adapt mathematics to the description of computer systems. The use of mathematics to describe computer systems also lends itself to precise formalism. This allows a clear, unambiguous specification of the requirements of software useful in large software development teams. The expressive power of Z also allows one to model not just computer systems, but systems of almost any kind. In particular, the accuracy and expressive power of Z make it useful for the description of safety-critical systems, such as banking systems and medical equipment. To see how Z is used in practice, let's model a transaction in a banking system. Z modeling is done by describing objects, such as data states, as well as operations on those objects, by means of a construct called a schema. A schema is represented by a labeled box that is open on the right-hand side. Here we model a client's bank account, represented as a data object consisting of the amount of money stored in the account. In the top rectangle, we declare the data elements used, the number of dollars and cents in the user's account. In the bottom rectangle, we describe whatever properties the bank account is supposed to have. For example, say we require that the balance never become negative. We express this by stating that in a valid bank account, the number of dollars and cents will be at least 0. This is an example of how an object is modeled in Z. Now suppose we want to model the act of withdrawing money from the account. This requires an operation on the bank account object and its data elements. An operation really just describes two objects, in our case one before the transaction and one after. The second object, here decorated with the prime symbol, represents the state of the system after the operation has been performed. The operation itself is described in its own schema. To indicate that we are modeling a transition from one bank account state to another, we include the bank account schema in the declaration box preceded by a delta. The delta indicates that we are describing a change between two bank account states. We also declare the amount of dollars and cents specified to be withdrawn by the user. Now we move on to specifying the properties of the transaction. We first require that the user not withdraw more money than is currently available. To do this, we specify first that the number of dollars withdrawn does not exceed the number of dollars available in the account. Additionally, we specify that if all dollars are taken out, the number of cents withdrawn does not exceed the number of cents remaining in the account. Next, we specify how the data elements of the state should transform upon a withdrawal of money. Depending on whether the number of cents withdrawn exceeds the number of cents available, we select the right relationship between the before and after states of the data elements. Notice how, in an operation schema, the data elements in both the before and the after state are included into the schema by the bank account declaration. This concludes our Z notation description of a banking system. This is just one example of how Z can be used in system modeling. The constructs demonstrated here are far from inclusive, and Z provides a rich mathematical toolkit along with a wide range of styles and notations. For more information regarding Z, check out The Way of Z by Jonathan Jackie, available from the University of Florida. Patrick Soupes provides an excellent account of Zermelo-Fraenkel set theory. The Z notation standard is also available as a technical document on ISO's website.